Hi students, it's Mr. Terrell, and I want to answer your questions about uncertainty and propagation of uncertainty. So the first thing to understand is there's two types of uncertainty. There's absolute uncertainty, and then there's percent uncertainty. The difference is absolute uncertainty has to do with the measuring equipment. So here's a scale, and when we turn it on, it says 0.00 grams. So I can know the absolute uncertainty of this scale by looking at the smallest increment that it measures, which would be here in the hundredths place. So this scale has a absolute uncertainty of plus or minus 0.01 grams. So for all digital equipment, it's very simple. You just turn the equipment on, you determine what's the very smallest value that it measures, and it's going to be plus or minus that value. But what about analog equipment? Well, analog equipment would be something like a ruler or a graduated cylinder or a triple beam balance, something that it doesn't just tell you the measurement, you actually have to use your eyes to visually inspect it and see where you're at. So the rule for analog equipment is you simply look at the smallest increment of measurement on that particular piece of equipment. Since this is a graduated cylinder, they usually measure in 1 milliliter values. So each of these represents 1 milliliter. So the rule for the absolute uncertainty inherent in an analog piece of equipment is simply 1/2 of the smallest increment. So 1/2 of 1 is 0.5. So this has an absolute uncertainty of 0.5 milliliters. It's as simple as that. This is the way it is. For every piece of digital equipment, it's the smallest increment. For every piece of analog equipment, it's half of the smallest increment. And that's it. So absolute uncertainty has to do with the device. We don't have to make a measurement. All we have to do is look at the device and find this information out. Now, percent uncertainty we actually have to make a measurement here. We can't find the percent uncertainty unless we make a measurement. So for instance, let's take our scale and let's say we put something on the scale and it weighs 10 grams. So what we have to do is first you have to know how to calculate percent uncertainty. That simply is the absolute uncertainty divided by the measured value, the measurement you make, times 100 because it's a percent. So if we put something on the scale and it measures 10.00 grams, what is the percent uncertainty? Let's work that out. So the absolute uncertainty is 0.01 divided by 10.00 times 100, and we get 0.1%. So that means when writing down this mass measurement, we would have to say that the mass is 10.00 grams plus or minus 0.1%. That's how we would write that down using percent uncertainty of this measurement. Now let's talk about, let's do another one. How about this graduated cylinder here? Let's say that we measure out 5 milliliters. So we look at this and we notice that the meniscus right here touches 5 milliliters. Now we know we can measure it to the tenths because our uncertainty here is in the tenths place. So we know that our measurement here appears to be 5.0 milliliters. But we want to know our percent uncertainty. We know the absolute uncertainty for this piece of equipment. We want to know the percent uncertainty for this measurement. So basically we use our formula here It's the absolute uncertainty, which is plus or minus 0.5, divided by the measurement, which is 5.0, and we multiply that by 100, and we get 10%. So we would write that measurement as 5.0 milliliters plus or minus 10%. And that's all there is to it. That's how you use or understand absolute uncertainty, which is by nature of the device, and how you use percent uncertainty, which takes into account the uncertainty of the device as well as the measurement that you made. So now let's talk about the propagation of uncertainty. So first of all, I think it's important to understand what that means. Propagation of uncertainty means when you're collecting data, each individual piece of data has an uncertainty associated with it. But the propagation of uncertainty simply means that as you have to add or subtract or multiply or divide these values in your processing of data, this uncertainty doesn't disappear. As a matter of fact, it becomes more uncertainty. The more measurements that you make, the more uncertainty you're going to have, because all of that uncertainty begins to compile and grow. So here's how that works. So there's two rules. The first rule is anytime you're adding or subtracting data, okay? And that rule says that all you have to do if you're adding or subtracting data is you have to add the absolute uncertainty for each measurement. That's not too bad. Let's do that real quick. So delta T is a common thing we do in science. We take the final temperature and we subtract the initial temperature. So let's say we look at our thermometer, and it's an old-fashioned glass thermometer, and we have to look at the mercury inside, and we make a determination. Well, first we have to say, well, what would be the absolute uncertainty of an old-fashioned thermometer that has 1 degree Celsius increments? Can you figure it out? Right. Half of 1 degree, which is plus or minus 0.5 degrees Celsius. Very good. So we look at one measurement. Our last measurement was 10.0 degrees Celsius. Our first measurement, let's just say, was 6 degrees Celsius. So we know we get 4.0 degrees Celsius. But the question here is, how did uncertainty in both of these measurements propagate through? Well, our rule says if we're doing addition or subtraction, which is what we're doing, we have to add the absolute uncertainty for each of these measurements. We know what the absolute uncertainty was when we made this measurement. It was plus or minus 0.5 degrees Celsius. We used the same thermometer, so the absolute uncertainty for this was plus or minus 0.5 degrees Celsius. So all we have to do, according to our rules, is add this uncertainty. So what we're going to do is we're going to write this as 4.0 degrees Celsius plus or minus 1. 1 degree. 0.5 plus 0.5 is 1. So there it is. That's how you propagate uncertainty when you're adding or subtracting. There's only one other rule, and that's when you're doing multiplication or division. So, for example, let's say, the rule says when you're doing multiplication or division, you add, here we go, the percent uncertainty. So that's an important distinction that you must make. If you're adding or subtracting, you're going to be adding absolute uncertainty. If you're doing multiplication or division, you're going to be adding percent uncertainty for each measurement. You have to, be detailed here. You have to be systematic. You have to be careful. And if you do that, it should be no problem. So let's do a measurement of density. And let's say we have to take a mass measurement and we have to take a volume measurement. And we're going to calculate density in our experiment, let's just say. So we know that our measured mass has a certain uncertainty. We know our measured volume has a certain uncertainty. And let's just go ahead and let's just say we have 10 grams of a substance. And we know that using our scale from earlier, that 10 grams of substance has an absolute uncertainty of plus or minus 0.01 grams. We know we're going to end up dividing this. Then we measure out the volume of that substance in our graduated cylinder from before. So we measure the volume to be 5 milliliters. And from before, we're using the same graduated cylinder. We know that the absolute uncertainty of that cylinder was plus or minus 0.5 milliliters. So the math here is easy. 10 divided by 5 is 2 grams per milliliter. But the question is, what is the propagation of uncertainty through this calculation here? Let's go back to the rule. You add the percent uncertainties. Okay, well, this is not percent uncertainty, so I can't add this to this. This is absolute uncertainty. So what I have to do is I have to go back and do those calculations for percent uncertainty. So for mass, it's 0.01. That's the absolute uncertainty of this measurement, divided by this measurement, which was 0.1%. And I'm going to add that to the percent uncertainty for this measurement right here, which would be 0.5%. I'm sorry, not 0.5%, plus or minus 0.5. That was the absolute uncertainty, divided by 5.0 milliliters. Sorry, I forgot to multiply by 100 here. Times 100. And then I get 10%. So I have to add this percent uncertainty for my volume measurement plus this percent uncertainty for my mass measurement, and I will get plus or minus 10.1%. Now let me ask you a question. Where is the most error being introduced into our study here, into our objective of our exploration of determining density here? Right. It's very clear that we're limited by our volume measurement. Mass measurement, that's pretty good, only 0.1%. But when we go through our study and we come up with our final values and we see this amount of uncertainty and error in our measurement, in our process data, it's good for us to explain within our conclusions the greater factor. One of the things to explain is a great factor was I was limited by my ability to measure volume, much more so than my ability to measure mass. So if I could have used a volumetric pipette or some type of better device to measure the volume of this substance that I was finding the density for, I can be that much more certain that this is a better value with a lower percent error, percent uncertainty. Remember, if you're an IB, you don't want to use milliliters, you want to use cubic centimeters, which equals a milliliter, so you only have to change a unit. Just like a cubic decimeter equals a liter, so you don't have to change a number, just change the unit. I hope this helped, and great job. Keep the questions coming, and I can keep making these videos to help you out with whatever you need. Have a great day.